Hello, welcome to the latest episode of Data Unchained. I'm the host, Molly Presley. If you haven't listened to Data Unchained in the past, maybe today's Hammerspace announcement is bringing you here for the first time, let me give you a little bit of information about what this podcast covers. We really look at the fact that over time, data has become an increasingly decentralized resource. If you think back to the days of mainframes being built and an entire building being built around them and all the people being close to them, to the way the world works today, where data is being created in devices, at the edge, in space, in clouds, in multiple data centers, kind of all over the place. We have the opportunity to get a lot more data and insights, but it's also a challenge on how do you harness the value of that data. Data Unchained digs into the challenges as well as the solutions and the really business upside you can get if you solve this problem. So without further ado, let me introduce today's guest. David Flynn is the CEO and founder of Hammerspace. He's been on Data Unchained a couple of times in the past, so he's not new to the show, but maybe new to some of the audience. So David, maybe just tell us a little bit about you and your history, and then we'll jump into the topic for today.
Oh, that's a wide-ranging question, but a little bit about me personally. While I am CEO and carry that title, I'm a technologist, a software engineer. Cut my teeth in the world of high-performance computing, and then had the fortune of being sort of at the forefront of the modern SSD era. Founded the company Fusion.io, which introduced the first truly modern, high-performance, highly reliable SSD, and in particular, directly on the PCI Express bus. So we pioneered what became NVMe. And as an outgrowth of that, especially since I'm a software guy, and that was really a means to an end in building the hardware, unlocking, performance in this new media, I set out after that to solve the challenges of how do you deliver the kind of performance that Flash and NVMe in particular has to offer. So that's a little about me and the mission.
And I think that history ties in particular to today's announcement that Hammerspace has put out there, and we'll be touching on that through the rest of this podcast. So today, Hammerspace announced a Tier 0 capability as part of their global data platform. We're going to be delving into that announcement, what problems it solves, and the technology behind it. So here we go. David, talk us a little about the problem that exists with GPU servers today, really any compute servers that are being deployed for things like AI and HPC.
Well, it's not uncommon for these systems to come with a large amount of storage capacity in each one. It's typically NVMe, my beloved creation, is inside of each of those systems, and often in large quantities. DGX nodes, HGX nodes, they come with flash devices, and often 30, 60 terabytes worth of flash. And more so, they come with slots to put in up to like 8 of these devices, which at these types of capacities, you could have half a petabyte of flash in each of those DGX nodes. The challenge is it's pretty useless. What do you do with an island of DAS, direct attached storage? I mean, little islands of data. So we talk about that as a issue of trapped capacity that's not doing you much good.
And as you think about that problem kind of obviously becomes even more substantial at scale. If you only have one server node and having direct attached storage within it is fine. But when you start to talk about tens or hundreds or even thousands of these and you're trying to put them in a workflow together, it effectively becomes impossible to manage. Would you agree with that?
Well, yeah, or tens of thousands like Elon is, or the big web guys. That is a lot of capacity. It's, if you start adding it up, it's in the tens of petabytes, hundreds of petabytes, even exabytes of storage capacity that is otherwise unused or underused on those nodes because it's very difficult to get use of local data that's local to the node. It needs to be shared so it can be managed globally and accessible globally.
So Hammerspace Tier 0 is technology that a couple of your teams have made possible. Partially the group who does contributions into the Linux kernels is also the Hammerspace team that develops the global data platform. But I would say it's very fair to say that it's due in large part due to feedback from customers that we work very closely with.
That's right. At the heart of the Hammerspace platform is the Hyperscale NAS capability, which allows you to use anything that speaks NFS as your storage, and in a way that you can scale it linearly. You can have 10 of them, you can have 100 of them, you can have 1,000 of them, you can have 10,000 of them, and the aggregate performance you get is 10,000x. Because there is no choke points between clients and those storage nodes. It's directly routed. So that hyperscale NAS architecture offers an opportunity because the machinery already exists in Linux to export local storage capacity, this local NVMe capacity, as an NFS file store. It's just thousands of tiny little NFS file stores wouldn't do you any good. So what the Hyperscale NAS Hammerspace data platform can do as a control plane sitting off to the side, it can aggregate those all into one massive shared storage system, one massive file system with the full aggregate performance of all of those storage nodes. And the fact that those storage nodes happen to be the compute nodes too is just fortuitous. So you can have the data be co-local, potentially to some of the compute functions that might be using that. And if it's not, then it's peer-to-peer between those nodes on your high-speed networks that typically unifies all of your compute nodes.
So I believe you were talking with one of the Hammerspace customers about this latent but available capacity in their nodes. And they really had a pain point of, yes, they had a lot of NVMe, tens of petabytes that it would be nice to use, but they needed to get into the market. They were under a lot of pressure to get their infrastructure up and running. Maybe just share that story a little bit. I know we're not really allowed to talk about the customer name specifically, but I think sharing that story helps bring to life how the innovation occurs in Hammerspace and why this is so important.
Well, it points out some of the key things here. And number one, they didn't have to deploy any special software. All they had to do is to turn on the NFS server on those DGX nodes, exporting that space, and tell the Hammerspace platform, the sideband control plane, about that space. And then Hammerspace, through its orchestration capabilities, can orchestrate and distribute the data, redistribute it, rebalance it, performance balance it, capacity balance it, and blend it with purely dedicated storage or even object storage. So the reason why we talk about this as tier 0 is that it's actually in front of tier 1. We have tier 1 storage, that primary shared storage. Let's call this dedicated storage, shared storage systems. And you have tier 2, your capacity tier, maybe it's S3 or object storage there. Well, this allows the data to be promoted to reside in the compute layer itself. It's not a cache, though. Those are actual instantiations of the file, which can be referenced peer-to-peer. As a matter of fact, you don't have to have tier 1. You don't have to have tier 2. But the thing about this is it's so easy to deploy because all of the machinery is built in to Linux that the time to value is nearly immediate. You don't have to go worrying about deploying custom software that's going to hog your CPU or software that has to go inside of your kernel that's going to not be compatible with your GPU drivers and all of that mess. This is just the innate capability that already exists within Linux to serve NFS and to be a client to NFS. But in this case, it's to parallel NFS and is able to use this sideband control plane. Think of it like DNS for data. It's routing the access so that the files can be distributed across the individual storage. The key thing here is, with this customer, it was about time to value. They had spent a lot of money buying a bunch of GPUs. And then the realization is, oh crap, we need some way to feed these things with data. We need a shared data platform. And then it's like, well, do we go and buy some shared storage? And, I just spent, most folks are really stretching their budget to be able to get the GPUs. The last thing they want is to have to spend a whole bunch more, or even worse, their power budget, because you've used up all of your power. You're going to hit your power cap when you put in GPUs. What are you going to do to feed the storage? Well, the beautiful thing here is this is a zero additional footprint. It comes built in. It doesn't take any more networking. It doesn't take any more rack space. It doesn't take any more power. And generally, the flash storage capacity is already a sunk cost and already exists inside the nodes. If not, you can add if you need to. That hasn't been the case so far, because most folks have found that there was an excess of their needs already sitting there. Now, the beautiful thing is that because this is part of an orchestrated environment, it's just one tier out of many. You can have a capacity tier, and that could actually just be the cloud, where your overflow data just goes off into S3 or some such. So it gives you that imminent flexibility. But the main things that were really in play here is how fast they could run it, because it's NFS. Everybody knows how to run that. It's not one of these exotic file systems where you need people that have the skill set to do that. And it's not like you had to deploy custom software or any of that. It's easy to use, quick to get up and running. That, I would say, was probably number one. Number two is, it's hard to say whether it was the cost avoidance of additional, external storage, or whether it was the power avoidance, not having power budget to put in additional stuff. But we shouldn't forget kind of the fourth, which turns out to be one that falls out in the wash, as it were, and that's the performance. Because now you're keeping those GPUs busy 100% of the time, because the data is closer to where it's being consumed, potentially on the same node itself or across peers. And with data orchestration, you can maintain multiple instantiation of the same file across many different nodes. So you get instead of one node or one shared storage system serving it out, you could have 10 copies or whatever. And through orchestration, that happens automatically. It's all one file. It's just instantiations of that file that happen automatically to amplify the bandwidth through. So files that are frequently read, all of those Python files that have to get read over and over again, those sorts of things, they can be preceded in a way that's distributed multiple times, so that you get not just local access from the guys that happen to have a copy of it locally, but at least near peer access with access from the neighbors nearby.
And you've done some work to even accelerate within each of these servers the data path. And if anybody's heard David talk at various industry events and whatnot, there's a mentality at Hammerspace to kind of chase the network hops and the latency of the data path in a lot of our architecture. And there's another innovation here. Right? A bit maniacal.
We're maniacal about getting rid of data retransmissions. It's how many times does the data have to be retransmitted to get to its destination, or to get from its destination into the storage if you're writing. You got to get rid of those. That's the number one thing you can do to improve performance, because it improves bandwidth and IOPS, but more importantly, it improves latency. And latency is the hardest one to get rid of. This is the only way to get rid of latency, is to get rid of the retransmissions. So again, this goes back to why I started building Hyperscale NAS and took the seeds with Parallel NFS, having come from Fusion.io, where we introduced NVMe, and the best place to deploy NVMe is in the servers that are using the data themselves. But to use that and have to forego the convenience of it being shared data is just too much of an ask. So how can we have our cake and eat it too, have it be shared data, but get the performance of local NVMe? And what I realized is we need to use the standard NFS machinery, because only then can we pull the following hat trick? And this technology is just going upstream into Linux. It's called the local I/O patch set. What it does is the NFS stack recognizes that the client and the server are on the same physical host. And the entire NFS stack steps out of the way, and the I/O requests go directly across the kernel by pointer to memory buffer, 0 copy. The net result of that is you do get the true performance of local NVMe access. It's like you're accessing DAS, even though that file is a shared file on a shared file system that just happens to be, fortuitously, thanks to Hammerspace, positioned on the node itself. So this ability to promote the data to tier 0 and potentially make it co-resident with the clients using it is very powerful, because networks, while we have very high networks in the modern world, 100 gigabit, 200 gigabit, 400 gigabit if you want, that pales in comparison to the performance you can get from an array of NVMe in the server. If I have just 8 NVMe devices, if those are Gen 5, it's like, crazy, 16 gigabytes a second. No, it's more than that. It's, 8, 32. Yeah, anyway, the PCI Express bus has massive amounts of bandwidth. It's, a crazy number of lanes. In that case, it's 32 lanes of Gen 5 PCI Express. You're not going to get that out over a network. I don't care if it's even InfiniBand or whatever. You're talking about hundreds of gigabytes per second of bandwidth and tens of millions of IOPS that you can drive against persisted data. And you can't do that over a network. So tier 0 is like a cache in that it serves the function of having promoted the data to near, but it's better than a cache because it's an actual referenceable copy of the data that adds reliability to it and can be accessed by peers as well, and is a full instantiation of that data, not just a partial pieces of it.
So when you think about storage infrastructure, a customer now can have this NVMe that's local in their server nodes. It could be local to GPUs, CPUs. It doesn't really matter which type of compute. And you think about these server nodes, you're now using this local NVMe as part of your shared storage pool with really interesting performance attributes. And then, so in addition to growing your shared storage pool, you also have this speed within the server where you're really keeping your GPUs efficient. So it's kind of a best of both worlds, whether you're working on shared storage capacity or really trying to feed your GPUs fast. So that's interesting to think about how within the server nodes or across server nodes you can protect the data. Can you protect the data using some of the other storage systems that are built into the data platform?
Well, that's right. With data orchestration and with objectives, you can set it up so the data is not just distributed across the DGX nodes or your compute nodes, but they can be mirrored to dedicated shared storage. And they can be tiered off into object storage nearly immediately. So whether it's synchronous for high availability or asynchronous for disaster recovery, you can have the exact same files have instantiations on tier 0 as well as on other tiers, like on your cheap capacity tier. And that way you can avoid one of the challenges of HCI storage infrastructure, risk of disaster within that same compute cluster, because now the data is replicated potentially synchronously. Of course, that's going to slow down your writes a little bit compared to writing locally and maybe to peers. But asynchronously, if you simply set up the objective so that shortly after the file is completed, it gets replicated elsewhere. Now, where this comes in really interesting is with checkpointing, because you can set up objectives such that the checkpoint gets affinitized and written locally and non-redundantly. So there is no over the network. You could basically be dumping memory to NVMe, but because this is on Hyperscale NAS and data orchestrated, your objective can say once that file's closed, use the data movers to silver it to create instantiations on the back-end storage and even move it off of the local one. So you didn't have to do anything. All it did is open a file and write it. And it's the policy that basically said, let that write happen against direct attached storage locally. And only later use the data movers to pick it up and move it elsewhere and get it off of that node. And it's moved logically. I mean, it's moved physically, but logically, it's the same file. It wasn't a copy of the file. The file wasn't moved anywhere. That checkpoint is where that checkpoint was. It always was placed in the shared global file system. That's where it exists. It's just for the first little bit, it was resident only on the node itself. And after a little bit, it became replicated to or moved to other nodes for reliability purposes. Now, why does this matter? Because checkpoints, your GPU cluster is sitting completely idle until they all get it written. And if they're all slamming the shared storage system, that takes a while. If they're all going to direct attached, super fast. So this is just one of those cool things that fall out of tier 0 is local checkpoint writing with lazy eviction of that checkpoint to somewhere safe where you can restore from. It just works like that.
So it solves the Jensen problem of an idle GPU is a sin. I think that's a quote that's floating around from him right now. It was another way to help in keeping these GPUs busy.
I thought you were going to say the Jensen sin where the GPUs tend to blow up a lot.
Oh, well, that too.
You need to roll back.
Either one.
If one sin is to have them sit idle, the other sin is to have to
blow up.
have to roll back because they don't function all the time. Reliability issues. There you go.
Absolutely.
Yeah.
Thinking about this type of infrastructure, some people listening to this may be thinking, is this like a hyper-converged model? Is it different in some ways? And as they've thought about why they haven't used this local NVMe in their servers so far, how are we overcoming those concerns?
There are valid concerns with HCI-based storage. Some of those concerns are complexity in the software stack and needing to drop in drivers and the compatibility of those drivers with the versions of the software and with the kernel. And this is where it comes in. In tier 0, using NFS, all of this machinery is built into Linux. And all of those capabilities exist all the way back to RHEL 7 timeframe. It's ancient. So all of this stuff is already built in. There is no issue with software versions, all that kind of stuff. A second concern has been the noisy neighbor problem. Serving peers would distract the CPU. I'd say this is one of the largest concerns. The interesting part about tier 0 and the fact that this is native Linux is that this is all handled zero copy in the Linux kernel and is extremely efficient. What we've seen is, well under 10% CPU utilization, even when serving data at full tilt to out the node. So it's highly economical on the CPU, very efficient at getting data out on the wire, more so than anything else is. So that's the second piece, is very efficient. And by the way, if you've distributed multiple copies, then that load isn't all on one node, right? But it's diffuse across them. And if you've distributed enough, it could be that it's co-resident everywhere. Let's say you have a 10-node cluster. You can set it up so things are 10-way mirrored. Nobody's having to serve to a peer at all. They're getting local access. So for relatively small-sized clusters, it can make sense to have, these things actually replicated enough so that everybody's getting access to a local copy. And oh, by the way, through the file system, it's just one file. It's not like you're having to maintain that. The system is doing it for you just by giving it an objective that says, I want this to have sufficient performance. It will automatically infer from that and create the instantiations necessary so that everybody has a local copy. So there is no having to serve to neighbors. There is no noisy neighbor problem. You get to pick and choose which one you want. Another concern with HCI storage is that it's an island unto itself. And now to scale capacity in your storage, you also have to scale. You have to scale the compute. You've coupled the scaling. Well, with tier 0, it's a tier among many in an orchestrated environment. So you can have a capacity tier. You can still have dedicated storage nodes that are high capacity nodes. You can have object storage. You can scale capacity independently of that. As a matter of fact, you can come to the table with your existing storage. With Hammerspace, you can use whatever file or object or block storage you currently have. So it's not like this is competing to be the silo to hold your data. You don't have to copy stuff in and copy it out. It's part of a continuum that can incorporate all of your existing storage. So being part of a data orchestrated environment gets rid of those concerns. It's another reason why this isn't HCI storage. It's tier 0 in a data orchestrated world where the data can exist on many different tiers and on existing storage. And that actually is relevant, by the way, for some of these customers that have gone, because they've already purchased some shared storage already. And, they run out of space on it, and then they need more space. And, Hammerspace can just say, well, let's add the node local storage into that environment, and boom, you've just doubled the amount of space you have, and with something that's actually higher performing. So, other concerns that people have is, what about the reliability? Because dedicated storage can be considered more reliable than your compute nodes, especially when you're shoving 8 GPUs in a server. And with that kind of power density, you're going to have failures there. And probably higher failure rate than dedicated storage systems. So one of the most important things to making this feasible is having both having redundancy in the data, n-way redundant data, which we do, and people typically run it, 3-way redundant, and having very rapid rebuild. So that should a node go offline or become unresponsive, the system will immediately be getting data from one of the others and be able to rebuild that data in very short order. So rebuild times matter, detection and failover times matter. And this is where our work with Meta at scale for their training environment was very, very valuable. We got to where we had thousands of storage nodes and the across their environment, and failures were are non-event. It's they architect their stuff like a website where nodes can come and go. The system needs to cope, and you could have a whole power rail fail at once. Things could be flaky on the network. And our goal, which we achieved, was if you have an outage, even a massive outage, that it take less than 10 seconds for the system to detect that and be using alternatives and to be, continuing on about life. And that it take less than 10 minutes to do the rebuild and to be back at full performance. And we got there as well. So it's super important in an environment where you're using node local as reliable shared storage to make it reliable. and this is a key to that. So reliability, noisy neighbor, software, those are some of the key challenges that we're faced with HCI storage.
So I want to ask a question about the noisy neighbor bit, and just because this is different than the way than storage systems have been architected in the past, I want to call one thing out. Usually to take advantage of something like this, you would be thinking about putting some client software on this storage system. And that's how parallel file systems would access potentially this kind of storage. They still don't have data orchestration, some of the other technologies you're talking about.
Not just the client software, but the storage server software.
And
they'd have to co-locate the storage server software if they're going to do this. Yeah. Mm-hmm.
So, and that's been a problem. We've heard from customers, they don't, like you say, they don't want the noisy neighbor. They don't want their compute resources being taken up by that type of software. How does Hammerspace overcome that? And I know you've kind of touched on that, but I just want to say, have you speak very clearly to that specific topic.
Yeah. So very clearly, number one, it's much more efficient because the storage serving is kernel-based, doesn't have to go to user space. So you don't have to do silly things like pinning a CPU in a polling loop. People who use RDMA and networking directly from user space end up having to do that because you can't route IRQs. So they literally have to burn whole CPUs. The only way around that, though, is to be in the kernel and to be able to get IRQs and to be able to do this, fast that way. So that's the number one differentiation, because NFS is built into Linux and in the kernel, and it can use IRQs. Those are the interrupts. You don't have to burn CPUs and polling loops to do user space networking stuff. Yes, SPDK is fast. That's the library from Intel. But it's a pig on the CPU to get there.
Gotcha.
Right? So, but what's built into Linux doesn't have that. So that's probably key number one. Key number two, unlike shared storage where you go to some storage node to get it, this can have the data distributed redundantly, and in the limit redundantly to where nobody's having to go to a neighbor. And one way to get rid of the noisy neighbor is not have to go to the neighbor, right? So it's very different, and that's only possible because this is data orchestration, and we can manage the number of instantiations of a file. And even if you don't go to that full extreme of having an instance for every node, you can go to where you have sufficient numbers of instances that they're not having to serve so many neighbors, right? And that means you can basically dial it where you need to be there.
All right. So thank you for sharing that you are indeed a technologist, not just a CEO. It is important. No, and that's where I wanted to go with that conversation is, we get questions in the industry as new innovation comes about. People try to liken it to things they know, and understanding, I think, for the technologists who listen to this show, how this is different from the way they know and have done things in the past, because it is different and it's already there in their Linux machines, is a big thing to understand. And I wanted to really have a chance to emphasize that.
There's one other point that just remembered, and that is that this does support RDMA networks because the Linux kernel and NFS kernel client and server supports RDMA. But again, because it's in the kernel, how pages get pinned is actually much more dynamic because it's the thing that manages pages, right? In user space, you have to dedicate pages and get them pinned by asking the kernel to pin them. And once you have them pinned, they're stuck. So doing RDMA from user space has its drawbacks, and doing it in the kernel makes it much more dynamic, more efficient use of those limited resources, and to get much higher throughput out of it. So this is one of the other reasons, is the ability to use RDMA, which distracts the server less, gets it out on the wire, is a little more efficient than, say, TCP/IP offloading. But that is another important key. If you're looking at really reducing the amount of load, think of it like what NVMe over Fabrics does, right? But now for NFS and file data, because it's coming over RDMA. Anyway, so really, really an important point there too.
This sounds like it could be complex, but I want, and we started out talking about how it's really already just there, and how you can leverage the DGXs. Let's just say, for example, talking about a specific type of compute node that you already bought today. What does the deployment scenario look like if they've already if a customer already has some DGX up and running, for example?
So if they already have DGX up and running, you deploy the Hammerspace metadata service on a virtual machine. That makes it really easy to spin up on physical hardware. In the cloud, you can do it on cloud instances, in a container environment. Basically, you spin up the Hammerspace control plane, and you tell it about the different file stores that you have available. And we aggregate those into a single aggregate namespace and distribute the data across it through objectives and policy. So doing tier 0 is as simple as NFS exporting the local NVMe space. Put a file system on it like XFS. We recommend. It's very fast. You could use EXT. You could whatever file system you want. Export that as NFS storage space. Tell Hammerspace about it, register it with Hammerspace, done. That's it. Objectives and so forth will know, how to place and distribute the data to achieve the stated objectives, levels of performance, levels of reliability, et cetera, et cetera. So it's really that easy to do across potentially thousands of nodes. You need that to be easy. And if all it is turning on the NFS server on those thousands of nodes. Now, if you've got an RDMA network and all of that, it's really rather simple just to make sure that those are RDMA exported. Nothing special needs to be done there, generally speaking. It's up and running very, very quickly. That's why it's all about time to value and the amount of work, because don't need people spending time on this when they can be spending time on, getting more GPUs installed, getting more stuff up and running.
So you're talking minutes and hours to bring hundreds of servers online is generally the scope of time you're talking. Is that fair to say?
Oh, yeah. And the best part is you don't have to do burn-in. You don't have to shake out the flakiness in the hardware. You go deploy dedicated shared storage system. You're going to be weeding out the things that got dislodged in shipping and whatever. If you have your DGX nodes up and running, which by definition you have to before you're going to do GPU computing, then you've already done this work. So this also can't be, overstated how convenient it is. You don't have to roll anything into your data center. You don't have to make sure that all the kinks have been shaken out of it. It's the burn-in's already done. It's already there.
That's pretty amazing. So you'll be at Supercomputing next week. I know both you and Hammerspace will be. And I think the fairest call to action we could have for this show is swing by the Hammerspace booth, come check out if you've bought some DGX recently, if you have other compute nodes you're using that have different types of CPUs, no problem. This is, as long as it's Linux, it will just, the same concept. As long as
it doesn't even have to be x86. It could be ARM based, right? There's no software compatibility issues because there's no software edition that needs to be deployed.
Perfect. David, thank you for joining the show again. And this is amongst the most exciting news I think that we'll probably be seeing this year at Supercomputing as well. So we really hope that folks will swing by your booth and check it out at the show next week in Atlanta if they're attending.
All right. We're excited to see you all there.
Thanks for listening to Data Unchained, powered by Hammerspace. To learn more, visit hammerspace.com. If you have a guest you would like to hear on the show, email me at molly@hammerspace.com.